this is some work that we're doing in School of Digital Media Technology with a small, very small company in Cambridge called Nine Tiles. And very small, but they do have a very big profile and quite a big bit of history in the field of audio media. So this is looking at a unified low latency network architecture for multi-channel live and interactive media. One of the problems that we have with IP media, as you know, if you've ever tried to listen to two radios, one which is on long wave or VHF, just about to play the Big Ben bongs, and another radio which is DAB, the two never go off together. The DAB is always a little bit behind because of the media transfer over an IP over a packet network, not necessarily IP in this case. The media is subject to delays and latency. In a media processing system, this is due to the analog to digital conversion, and it involves digital consoles and computer systems and things like that. So anywhere where we have the process of having to go from an analog media into a digital media, we have to buffer the analog, do the readings, and that all takes time. If we're then going to send that through an IP network, then things get even worse because we then have the network routing and so on. So we have to buffer any incoming data at the network nodes, and to then route the information through that node and then on through the network to the next node. So the diagram here is sort of showing you what happens with a general network. We're trying to get audio, a violin player across the network down to the bottom left there, or we have some interactive TV taking place, and so we have some program which needs interaction, and all of these require, if we're going to get the best experience out of this, they require very, very low latency. The bit in the middle is a schematic of the Flexilink board, which we are working with and which we're doing tests on within the university with and on behalf of Nine Tiles. People involved in this include Leo Wang up there, and in a few minutes time I'm going to have my colleague Dalia Elmana, who's going to talk about her work, her PhD work on taking this a bit further and looking at the scheduling of this. Anyway, back to this. The problem is then that we do have latency in packet media, and particularly where that media is going to go over a network. And so what we want is difficult for the internet, the IP network that we're all used to try and support both time-critical data, like media, along with what's called best effort data. Best effort is the data which is the way in which the network will try and deal with data in a non-prioritized way. So basically, if you throw an email into the network, then you don't mind if that email gets through in half a second's time or even in 2 seconds' time. With time-critical data like media, then that half or 2 seconds, of course, is an eternity. And so connectionless, or that is packet-by-packet transport of data through a network is a problem, and particularly for this deterministic low-latency data, or the media data that we're interested in. The professional audio networking industry have traditionally had problems with this, and they try to, within their islands of usage, not network together across a national network, but within their own sort of islands of usage, they try to use customized versions of packet networks if they're going to use packet networks at all, and they're going to use these AES-50, EtherSound, CobraNet, and so on. For another sort of interest of mine is interactive TV, and if we're going to have any meaningful experience where we're interacting with something that's happening on the TV with other users at the other end of a link, then again this is another example of where we need this low latency, particularly if we're having viewer-to-viewer interaction. So we require this fast response on these carrier networks. Another problem that we could get is where we have multi-channel streams, particularly if we have ranges of sampling frequencies and variable bit lengths. There's a need for flexible routing and channel assignments, and current multiplexing methods are insufficient without sampling rate conversion and so on. So there's a lot of problems with trying to support this time-deterministic media data over the current network. So the Flexilink solution, and I'll say that is the board that is the current prototype board for this, combines what was called time division multiplexing, or TDM, methods with best effort networks. TDM is the traditional way in which networks have transferred digital data. So they're taking data and immediately assigning it to a known slot within a network transporting that across the network. The far end knows where to look for it and to extract it. And so we have a degree of control over any latency at all that's in that transfer. So the Flexilink solution is trying to impose that as part of the design, and therefore guarantee a quality of service, QoS, and an expected quality of experience, because we can calculate and know the data that's coming in terms of bit rate and so on, and therefore drop that data into this what's called a time deterministic bit pipe. So coming through the node, the network node, the Flexilink node, we have this stream of bits which we're going to use to take any time deterministic data and drop that straight into the, take it straight out of the incoming buffer and straight into the output buffer, so that we have as low a latency as possible for that, for transferred data over that node. Then around that, any best effort data which doesn't really mind about any sort of delay or any sort of latency, we can sort of start to pack that around the gaps within that bit pipe and try to, so basically we're intelligently using a scheduling format for getting that time deterministic data through that node and packing any best effort data around it. So Flexilink, it says at the bottom there, is basically defining the layer 2 protocols to do this and developing a prototype network processor architecture and the interface cards to do it. Layer 2 protocols, for those of you not into networks, these are the protocols which are to do with a sort of localized addressing, but particularly with the buffering and the framing of the data into data fields as it's going to be initiated, ready for transport across the network. So here we have an example. Now what I've got here is right at the top we have an incoming pair of ports. We have that coming through the Flexilink node and being pushed out down the bottom here into two output ports. So each input port we have synchronous flow data, that is the time deterministic media, and also the asynchronous flow data, which is the best effort stuff. And all of that is going to be recognized by the Flexilink node and routed accordingly. So in this particular case, over on the left, I've got a little routing table to tell us which synchronous flows are going to which output port, A or B, and again for the asynchronous flows that we have there. So essentially, we're defining these three packet categories: the synchronous flow, which is our time deterministic media data that we're interested in. There's the asynchronous flow, the best effort data, and there's a third type of traffic that we're interested in, which is the control messages, which are the messages which are in-house within the node itself and are keeping the housekeeping part of the node working. So the synchronous flows are shown there in the pinky red, and you can see that where possible they are within their particular relative part of the incoming node, they are dropped into the same relative part of the outgoing node. There are going to be gaps between them because they're arriving at different times, and within those gaps we're going to be dropping in as we can this best effort asynchronous flow traffic. So you can see that SF3 and SF2 are media messages, media sessions which are going out on port A, and SF1 and SF2 are going out on port B. SF2 is the same, is going to two different ports, because in this case SF2 is what's called being multicast. That is, it's being sent to lots of different people all at the same time. You can think of that as being something like a TV broadcast or so. Okay, so it's a bit like we're using this bit pipe coming out of the node a bit like a TDM system, a bit like a time division multiplex system. So basically we're allocating, we're knowing where the time slots are and dropping the synchronous flow packets into these sort of notional time slots ready to be transported out through the network. So asynchronous flows are dropped into the bits in between there, as and when they can be. It may be that an asynchronous flow packet needs to be split into two, so that half of it can be accommodated before a synchronous flow media packet and half of it afterwards. That's the sort of thing that we can do with this method of working. So in terms of the architecture, there's the control unit and the forwarding logic. And I notice that my time is magically up. So in a few minutes' time, my colleague Dahlia is going to more or less take over from that point and explain the research work that she's doing on the scheduling of these packets going through this control unit and the forwarding logic. Thank you very much.